Okay, in this video I'm going to go over the gravity worksheet. Gravity is the mutual force of attraction between any two objects with mass. So let's say we have two bodies, you and the Earth. And why do we call it the mutual force of attraction? Because the Earth's force on you equals your force on the Earth. These forces are equal but opposite. That comes from Newton's third law. When object A exerts a force on object B exerts the same force on A. Here's the equation. The force of gravity depends upon the product of the two masses involved and the distance separating them. R is the distance between the radial centers. So what does that mean? Here's R. Two bodies. Maybe it's the Earth and the Moon. This is R. So it's the distance between the radial centers. And that's why you standing on the Earth, your distance between the Earth and you is not 0, but it's R, or a little bit more than R, because it's the radius of the Earth and then the distance between your feet and the middle of your body. So nobody's going to ask you to plug into this equation, but you'll have to know the relationships. This relationship is inverse square. And what does that mean? If you triple the distance, then the force of gravity is 1/9. You double, it's 1/4. You multiply by 5, and it's 1/25. You quadruple, it's 1/16. Inverse square. F and M are direct. And the plot shape of the direct looks like this. And the plot shape of the inverse looks like, whoops. Okay, let's see. I told you you won't be plugging into this equation, but you'll be doing relationship questions. You've got M1 and M2. Distance R apart. There's a force of F. What if you double both masses and you change the distance to 4R? So how do you do relationship questions? You need the equation. You plug in the changes. Double, double. These are doubled. This is squared, by the way. I have a tendency to leave out the square. So this is quadruple. That's 16 on the bottom, because 4 squared is 16. 2 times 2 is 4. That's 1/4 on the right and 1/4 on the left. So the answer is that the force with these changes will be 1/4 of the original F, or 1/4 F. You've got a satellite, A, and it's right over here. It's got this force on it. It's the force of gravity. And what about B, which is at a distance of 2R? You can see it's 2R. So let's take a look at the equation. And what is doubling? This is squared. If you're doubling the distance, which this is R, this is 2R. You double the distance. This is 2 squared. There's no change on the top, so it's 1. This right-hand side changes by 1/4. And so whatever happens to the right happens to the left. So it's going to be 1/4 of the force. Well, this is 160. So the one that's 2R will be 40,000, because that's 1/4 of F. That's 1/4 of 160,000. So there's the answer to that one. We've got a rocket, 18,000. That's its force of gravity. This is not a rocket, but let's imagine it's a rocket. It's on the Earth's surface. What's its distance? R. There it is. It rises to a height of where its distance is 3 Earth radius above. Distance from the Earth is now, so it goes from R to 3R. distance 3 Earth radii. What will its weight be? Well, its weight is the force of gravity. Let's look at the equation again. So we're going from R to 3R. We're keeping the top the same, multiplying the bottom by 3. 3 squared is 9. So it's 1/9 on the right, 1/9 on the left. You were 18,000. 1/9 of 18,000. Your weight changes. The rocket's weight changes to 2,000 newtons, that is. When on the Earth, the distance, separation distance, or the R value is R, the Earth's radius of the Earth. Weight, as you know, is the net gravitational force on an object, and it depends on the G, where you are. If you're at the pole, your G is a little bit bigger. New York, it's 9.8. Denver, it's a little less. Denver's has a higher elevation, so it's further from the Earth, so its G is smaller. So you can see G depends upon R, the distance between the two objects, which is essentially the Earth's radius. You know, the Earth is actually a little flattened on the top. The R is bigger this way than it is this way. So you're at the North Pole, you're going to have a smaller R and therefore a bigger G. Okay, what explains the difference? Let's say different R, different separation distance. Weight is m times g, you know that, but it also equals this. These two are equal to each other. So you can cross out the m, mass of the smaller body, and you can see the g is that that constant, and mass of the Earth divided by r squared. M is the mass of the Earth or large body. You know, if you got problems involving Jupiter, the mass of Jupiter would determine the G. If you're near the Mercury, the mass of Mercury will determine the G, and certainly the R distance, the separation distance. Let me show you how this works. Like I said, you won't be plugging into this. So Mars has a mass of 1/10 of the Earth, and its diameter is 1/2 of the Earth. If its diameter is half of the Earth, its radius is also half of the Earth. Okay, so how does this go? Well, we're looking for the acceleration of a falling body. G equals gm. Well, for the Earth, r squared. G of the Earth looks like that. But since Mars is 1/10 the mass, and its radius is 1/2, but that gets squared, so that's 1/10 divided by 1/4, multiply top and bottom by 4, and you get this bottom clears out, and you get 4/10 on the right, well then 4/10 on the left. So what's 4/10 of g? That's g is 10, so it's 4 meters per second squared. So the acceleration due to gravity on Mars would be about 4 meters per second squared. Here you've got to calculate the force of Earth's gravity on a rocket ship. Find the force of the Earth's gravity on a rocket ship that's 2 Earth radius above the Earth's surface. Now, be careful with this one. So the rocket on the ground is R, but now it says 2 Earth radius above, so it's 1, 2, R and R. So now what have you done? You've tripled the R. So let's see how this works. Well, what is calculate the force of the Earth's gravity? What would it be at R? On the Earth would be m times g, which is 1350 kilograms times 10 meters per second squared. So on the Earth, it'd be 13,500 newtons. But that's not the question. The question is, what if you go 2r above the Earth's surface, really effectively tripling the distance. So let's go force of gravity. This is the equation that relates the force of gravity in r. So we're tripling the distance, not changing the mass of each of the bodies. So this is 1/9. So the right is changed by 1/9. The left is changed by 1/9. So we have to take 1/9 of 13. We have to take 1/9 of that. And so the new weight will be 1,500 newtons. So you triple the R, you're going to change the weight by 1/9. We're going to skip, oh no, we're not going to skip this one over here. A hypothetical planet has a mass that's 1.66 times the Earth. What is the same radius? What is the G? So we get our G equation. I want to remind you where we got this. The weight equals force of both of these things equal the force of gravity. The mass of the small body cancels out. The big body stays. So G depends upon the mass of the large body. So for Earth, this is what it looks like. But this planet is 1.66 times the mass of the Earth with the same radius. So bottom doesn't change. So this G is 1.66 G, or 16.6 meters per second squared. We're going to skip this. You're not going to get this is just a plug-in problem. You're not going to get a problem. You're not going to get a problem like that. Like that. Prove that the orbital velocity, V, of a satellite does not depend on mass. Well, if you're a satellite, you have a centripetal force on you. That is what? That comes from what? It comes from gravity. That is your centripetal force. So let's cancel out the mass of the satellite, because both of these equations have the mass of the satellite. And you know what else we're going to do? We're going to multiply both sides by r. This by r, this by r. So that r cancels out. And this becomes 1. So it's getting a little messy here. V squared equals gm over r, not r squared, because the r, one of the r's cancels out. So V equals radical gm, mass of the Earth, or the big planet, divided by r. Now, there's the proof. There's no m in the equation. The mass of the satellite cancels out. What does velocity depend on? We could see in the equation that orbital velocity and period only depend on what? On the mass of body orbited, the mass of the large body orbital, and the distance, the orbital period. So that is orbital period. I'm sorry, orbital radius, I should say. Orbital radius. That's not the orbital period. We'll talk about that in a little bit. You can see right here. So you have to be able to derive this equation. How? The centripetal forces comes from the gravity. The little m's cancel out. The large m, the large body being orbited, stays. That's this. Whether it's the Earth or the radius of the moon. I'm sorry, the Earth or the moon, whatever's being orbited, the body being orbited. Now let me show you about orbital period, because V is 2 pi over r. And, well, that equals radical gm over r. And so you can see, whoops, 2 pi. Well, that's not 2 pi over r. It's 2 pi r over t. V equals 2 pi r over t. So what does the period depend on? Well, look at the equation. Once again, it depends on m, mass of the body being orbited, and r and m. M is the large body being orbited. G is just a constant. It's a number. It's not big G. Let me clean it up a little bit. It's not little g, it's big G, it's constant. All right, let's figure this one out. The smaller the radius, the blank the orbital velocity. Let's look at the equation. The smaller the radius, oops, that's not the square. Get rid of that. So the smaller the radius, well, that's on the bottom, smaller the radius, the larger the velocity. The planet closest to the sun, Mercury, has a very small r and a very large velocity. It's the fastest planet. The last planet now is Neptune. Its radius is orbital radius is very big, and it's a slower moving planet. Inverse relationship. See that? Now, so the smaller the radius, the larger. The smaller the radius, the larger the orbital velocity. See that? Inverse. One's on the bottom, one's on the top. And the blank, the period. Well, let's take a look at this. What about the period? Well, think about it. Just use your logic. If the velocity is larger, then the period is smaller. Mercury is the fastest, and it has the smallest period. Takes the shortest time to go around. And that is it for this one.